In this video, we will cover an introduction to determinants. This is the overview slide, which will spend about 5 minutes just to get a feel for what the topics are of this video, and then we'll go back and cover each topic in more detail with more examples. So to start with, you may have seen determinants before. If you've done vector calculus, you remember the cross product was defined in terms of a determinant. Also the Jacobian, when you would do integrals, when you changed from one coordinate system, for example the rectangular coordinate system, to either the polar or the spherical or cylindrical coordinate system, you would use the Jacobian because the Jacobian gave you an indication how the transformation to one coordinate system to another would transform areas of a figure. The determinant will have a lot to say about invertibility of a matrix and about matrix transformations in general. In this video, we will start with the definition of a determinant of a 2x2 matrix, which is given with this formula here. Then we will go on to larger matrices and kind of have this sort of recursive definition of determinants. The next material, which might be new to you, is a cofactor expansion definition of a determinant. And then we have this theorem here for determinant of a triangular matrix. So if A is triangular, then the determinant of A is the product of the entries on the main diagonal here. And we'll do plenty of examples. We will start first with the definition of a 2x2 determinant. For a 2x2 matrix, which looks like A equals A11, A21 for the first column, and A12, A22 for the second column, the determinant will equal to A11 minus A22 minus A12 minus A21. So it's kind of like you multiply across the diagonal, A11 times A22, and you subtract the multiplication across the other diagonal, A12, A21. For n greater than 2, we define the determinant recursively. So it's the sum of the n terms of the form plus or minus a sub 1j. So this is the first row. So we're going across the first row, and we're going to multiply each term of the first row times a sub 1j, and this is the matrix a sub 1j, which is the matrix A with the first row and the jth column deleted. And you'll see because of the plus and minus, those alternate, where the entries A11, A12, and A1n are formed from the first row of A. So in symbols, we have the determinant of A is equal to A11 times the determinant of the matrix A11 minus A12 times the determinant of the matrix A12. And we keep alternating signs, so the nth term is minus 1 to the 1 plus n, A1n, times the determinant of the matrix A1n. We will use an example to illustrate how this formula works. So we'll look at the matrix A equals 1, 2, 0, the next column 5, 4, negative 2, and the last column 0, negative 1, 0. So according to our formula, and now I'm going to use the summation formula, we start off with j equals 1. So we have negative to 1 to the 1 plus 1, which is positive, so it's just 1. And then we're going to have A1j, so it's A11 times the determinant of the matrix A11. So this is the first term. For our second term, now we have j equals 2, so this becomes 3, so we need a negative 1. And then we have A, again 1, 2, times the determinant of the matrix A12. Now we have j equals 3, so this becomes 4, so this is a positive, and then we have A13 times the determinant of A13. So this negative 1 to the 1 plus j, it's simply the alternating the signs, as this says, with the plus and minus signs alternating. It is useful later when we do other row or column expansions, so it's worth kind of remembering this. Looking at this, so we'll have A11 times the determinant of the matrix A11. This is the matrix where the first row and first column are deleted. So I wrote down, I copied my matrix A here, and also this these straight bars stands for determinant. So we want the determinant of the matrix A with the first row and first column omitted. So I went ahead and crossed them out. And I also said, okay, this is A11, which I'm going to move here on the next line. The next one we have a minus A12, which I circled here. Later we'll move this 5 over here on my next line. Determinant of the matrix A with the first row crossed out and the second column. And then finally we have A13, which I've circled, I'll move it here, with the determinant of the matrix A with the first row and third column crossed out. And what I like to look, I have this circled because not only am I going to move it over, but once I circle the 1, it's the same row and same column as 1 that gets crossed out. Then I go, again, we're doing all the entries here of the first row of A. So my next entry is 5, so I'm going to circle that, but I'm going to cross out the column and row associated with the 5. And then last, I'm going to look at my last entry of the first row, which is 0, cross out the row and column. So you can certainly use these indices here, or you can just see that since this entry cross out the 0, the first row and the third column. Here it's first row, second column, and this 1 is first row, first column. So I rewrote this again. This is the A11 is 1, and then I have the matrix 4, negative 1, negative 2, 0, the determinant of 4, negative 1, negative 2, 0. Then here I have A12, which is 5, times the determinant, that's these bars here, of 2, negative 1, 0, 0, this matrix here. And then I have A3, which is 0, times the matrix 2, 4, 0, negative 2. So now I have 2 by 2 matrices, and I can use my formula over here. So this is 1 times 4 times 0, remember it's the cross multiplying, and the minus 1 times minus 2. And again, there's a minus sign here, so I have a minus, and then my minus 1 times minus 2. Then I have my minus 5, 2 times 0, minus negative 1 times 0, plus I just put the 0 here, and I didn't cross multiply for the determinant. So these terms are 0, and what I have is 1 times this term here, so negative 1 times negative 2 is 2 with the minus, so my final answer is minus 2. Next, we're going to look at this definition of a cofactor, which is useful later when we do these cofactor expansions. So the ij cofactor, which is designated with C of ij, is negative 1 to the I plus j times the determinant of aij. So if you look at what's going on here, we're taking this part of the formula, the negative 1, and then we're taking the determinant part here as the cofactor. So then what our determinant of A looks like is A11 and then the cofactor plus A12, and then we take the cofactor, and then up to A1n, this part, this negative 1 part, and the determinant part. So this is what the cofactor is. And then we're going to look at cofactor expansion. So the determinant of an n by n matrix can be computed by a cofactor expansion across any row or down any column. And that is to say, when we defined the determinant here, we went across the row and then multiplied by the submatrix when we crossed out the corresponding row and column. But what this cofactor expansion theorem says is we can use any row. We didn't have to use the first row. We could have used second, third, or fourth row. Or we can expand across a column. So instead of using rows, we could use the first column, second column, or third column. And this here gives us the formula for the determinant when we're using the ith row. And here's the formula when we use the jth column. And just a note, so this theorem is helpful for computing determinants of a matrix that contains many zeros. So in other words, well, actually I'll give you an example. So I have the definition of the cofactor here, and also the definition of our determinant in terms of the cofactor, and then I have the definition of the cofactor expansion of a determinant. So the example is to use a cofactor expansion across the third row to compute the determinant of A. A is equal to the matrix with column vectors 1, 2, 0, 5, 4, negative 2, and 0, negative 1, 0. So you could see if I had expanded across the top, I would have had my A11 times this matrix here, and then I would have had 5 times the matrix 2, negative 1, 0, 0, and then I would have had 0 times this matrix here, but 0 would have made this calculation easy because it would have just been 0. But you can see by expanding across the third row, now I have 2 zeros. So really all I have is this one calculation to do, which makes it easier, which is why the third row is easier. Also, you'll notice we could have done the third column and had these 2 zeros as well. But we're going to follow the instructions and do the third row. So now my ith row, so it's the third row, and I'm going to use my formula. Determinant of A is equal to I31 C31, so A31 C31, and then A32 C32, A32 C32, and A33 C33. So this is what our determinant looks like. And you can try to memorize this formula, but actually if you think about it, it's not that hard because you're expanding across the third row. So your A is going to go from, across the third row, the first column, second column, third column. So you have A31, A32, and A33. And then this matrix here, the C corresponds to whatever your indices of your A is. So if you have A31, then C is 31. If you have A32, then C is 32, and if you have A33, C is 33. So it's, you can memorize it, but it's actually not that hard to just kind of figure out. Plugging in the numbers, A31, so third row, first column is a 0. And then we have and I'm plugging it all in, even though at this point you really don't have to do anymore since it's times 0. But I'm just plugging it all in so you can see how the formula works. Now our C31 then takes into account first our negative 1. So I'm going to have my negative 1 and then 3 plus 1. And then I'm going to have the determinant of the matrix A with the ith and jth column deleted. So that's determinant of A and then with the third and first column deleted. This just matches here. Plus, now we have A32, again my negative 1 term, raised to the 3 plus 2, determinant of A, the matrix A32. And then last we have our A33 term, our negative 1 to the 3 plus 3, just these two added together, determinant of the matrix A33. Now I'm going to plug in the numbers. Third row, first column, that's a 0, times this would give me my positive 1, determinant of A31. So here I've copied the matrix A, and I put the determinant signs. So it's the matrix A with the third row, first column deleted. So this would be the matrix, except for the fact that we're multiplying by 0. So again, the idea is if we're at A31, that's this coefficient here, but then we just cross out the row and column that this A31 belongs to. Next we have A32, which is this term here, third row, second column, and we're going to cross out the second column, third row, but we also have our negative sign, which in this case is to the 5th power, so we have a negative 1. And then finally we have our A33, which again is 0, and then if I wanted to cross out, it's this 0 here, A33, I'd have to cross out the row and column associated with that. So if we multiplied out the determinant, if this weren't 0, this is the matrix we would be using. So I brought down my 0, my matrix 5, 4, 0, negative 1. My negative 2 times negative 1 will give me 2, with my matrix 1, 2, 0, negative 1. And then my 0 with my matrix, I didn't carry this over, with my matrix 1, 2, 5, 4. So these two terms go away, and I'm left with 2, and now I have a 2 by 2 matrix, 1 times negative 1, minus 0 times 2, so this is negative 1 times 2, and I get negative 2, which is the same answer we did when we expanded across the first row. This is actually the same example, the same matrix we did in our first example. And so this theorem is helpful for computing determinants of matrices that contain many zeros, because you can see we can save some of these matrix calculations. So for example, if the first row contains many zeros, then a cofactor expansion across that row will be easier to calculate. Here's another example where A has many zeros. So the first column vector is 3, 0, 0, 0, 0. The next column is negative 7, 2, 0, 0, 0. The third column is 8, negative 5, 1, 2, 0. The fourth column is 9, 7, 5, 4, negative 2. And the last column is negative 6, 3, 0, negative 1, 0. Because the first column has the most zeros, I am going to use cofactor expansion along the first column. So we're going to use this column form here. So this is our first example of a column expansion. So we're going to have the determinant of A. So now it's the column that we're holding constant. J is equal to 1, first column. So we're going to have A11, C11. Now we're going to have A21, C21, A31, C31, A41, A51. And so again, the idea is here, we're expanding along this column. So this entry is A11, and the C11 is the IJ is the same. And going down here, this is a second row, second row, first column, so that's A21. And again, C21 echoes that. And then this is the third row, first column, so that's A31 and then C31, A41, C41, and last, fifth row, first column, A51, C51. So again, you can memorize this, but it's also kind of easy to figure out. So just looking at this, my A21, A31, A41, and A51 are all equal to 0. So this whole expansion then is equal to A11, C11. And so I'm going to plug in, let's see, my A11, and then for my C, my cofactor, first I have to take care of my negative 1, so that's negative 1 raised to the 1 plus 1. And then I have my matrix A with the ith and jth row and column deleted, so that's A11. My A11 is equal to 3, and now I'm going to, and my negative 1 squared is just equal to 1, and then I'm going to look at A11. So again, I circled my 3, because we're looking at A11. I cross out the corresponding row, which is the first row, first column, and this is my remaining matrix, which I wrote over here, my 2, 0, 0, 0, negative 5, 1, 2, 0, 7, 5, 4, negative 2, 6, 0, negative 1, 0. So now this is my A11, and I'm going to expand here because I need to figure out the determinant. I'm going to expand along the first column. Again, there are many zeros. So I'm going to bring over my 3, and then the determinant of this matrix now is going to be similarly, it's along the first column, so A11, C11, again, because I want this term, and then I want this term here, which is A second row, first column, A21, C21. This will be A31, C31, and A41, C41. And again, the A21, A31, and A41, these are all equal to 0. So I'm left with is my 3 times my A11. And now this A11, by the way, is referring to the first row, first column of this matrix. So that'll be 2 times my C11, again taking care of my negative 1, raised to the 1 plus 1 is 2, and then A11. And again, this matrix now refers to my new matrix. I hope this isn't too confusing. I have referred this now as my matrix A, not the original A. This is this matrix here. So now I have 3 times 2 times 1 is 6, A11. Now I need to find my A11, which is this matrix here without the first row and without the first column. So my new matrix is 1, 2, 0, 5, 4, negative 2, 0, negative 1, 0. Looking at this matrix, since there are 2 zeros in the bottom row, I decided to expand along the bottom row. So I still have my 6, and now looking at the bottom row, the first term is my A third row, first column, that's A31 times C31. My third row, second column, that's A32, C32, and then A33, C33. So again, carrying over my 6, my A31 is equal to 0, my A32 is equal to negative 2, and now I need my negative 1, and in this case it's raised to the 3 plus 2 power, which is 5, and then my A32. Here my A33 is equal to 0, so I carried that over. A32 now looks like, delete the third row, second column, and that was with the 2. So my new matrix is my -2 times 6 times -5. That's 12 times the matrix 1, 2, or the determinant of the matrix 1, 2, 0, -1. And now I'm at a 2 by 2 matrix, so this is 12 times 1 times -1, which is -1, minus 0 times 2, which is 0, so my final answer is -12. Next, I have this theorem concerning the determinant of a triangular matrix. So if A is a triangular matrix, then the determinant of A is the product of the entries on the main diagonal. And I'm going to show you an example to give you an indication of why that's true. So here we have a triangular matrix. It's 5 by 5. So I have A11, A22, A33, A44, A55 across the diagonal. Underneath I have zeros because it's triangular. And then above the diagonal we have other entries. We're going to then determine the determinant of A. We start by expanding along the first column because there's a bunch of zeros there. So that means the determinant of A, so in the first column we have A11 times C11, A21 times C22, A31 times C31, this is the fourth row, first column, A41, C41, A51, C51. And here we have A21, A31, A41, and A51 all equal to 0. So this comes down to A11, C11, plus all the zeros. And then to calculate our C11, well, that will be -1 to the 1 plus 1, which is squared, times the matrix A11. And I can circle my A11, and I'm going to cross out the first row, first column. So here is my remaining A11 matrix, and my A11 is circled. So I brought down my A11, and now I copied the -1 squared is just 1, and I copied my matrix A11, which looks like A22, 0, 0, A23, A33, 0, 0, A24, A34, A44, 0, and A25, A35, A45, and A55. So here I have that determinants, the determinant signs as well. So next, looking at this, again, I'm going to expand along the first column. So I have my A11 here. And now I'm going to use my formula to expand along the first column. And so the tricky part here is now I'm going to refer to A11 because I want the first row, first column entry, even though it's called A22. Imagine this is a number, right? If it were a matrix, this would be the number 7. But I want this element. So by A11 here, it's not the same A11 as this. This A11 is the value of my first row, first column. This is the first row, first column of this matrix here. So hopefully that's not confusing. So to expand along the first column here, I'm going to have my A11 times C11, A21 times C22, my third row, first column, A31, C31, and fourth row, first column, A41, C41. So now I have my A11. This here, first row, first column, is actually equal to A22 times my -1. 1 plus 1 gives me the squared. And then my my matrix A11. Here I have A21, A31, A41. These are all equal to 0. So I have A11, A22 times my matrix A11. And in this case, again, this is the matrix we're talking about. Subtract the first row, subtract the first column, and this is the remaining matrix. So here I have this A11, A22, and my remaining matrix is A33, 0, 0, A34, A44, 0s, and A35, A45, A55. You might take a look and see where this is going because we are certainly getting the entries on the diagonal as our determinant, but we'll continue. I needed some space, so I moved one of the matrices over here. So this is the last matrix we were looking at, A11, A12, and then this matrix here. So again, to expand along the first column, we're keeping our A11 and our A12, and the determinant here, when we expand along the first column, is our A11 entry times C11 plus our A21 entry times C21 and our A31 entry times C31. So that's A11, A22, these two go to 0. Here our A11 entry is A33. We have our negative 1 to the 1 plus 1 squared, and our A11, and then our 0, 0. And our A11, again, is our first row, first column are deleted. And now we're down to a 2 by 2 matrix. Again, I kind of moved this matrix over to make a little more room. So we have A11, A22, A33 times 1 times A11, which is our A440, A45, and A55. Now we do our cross multiplication. So we have A44 times A55 minus our cross multiplication here is 0. So our final answer is A11, A22, A33, A44, and A55, which are exactly the entries along the diagonal. So we haven't proven this for an n by n, but we did show it was true or proved it was true for a 5 by 5. This was an example we had done previously, so we're not going to look at it again, but we have finished the ideas in this video. So I have one more problem for you to try. So because we've gone through all the material, after I give you the problem statement, I encourage you to try it on your own, and then when you come back, you can check your answer against the answer I have. But also remember, you might have had different expansions along different rows and columns, but you can still see the final answer and see if it's the same. So the problem is to compute the determinant of the matrix with the column vectors 5, 0, negative 5, 0, negative 7, 3, negative 8, 5, 2, 0, 0, 0, and 2, negative 4, 3, negative 6. Because there are so many zeros in the third column, I chose to expand along the third column and I circled it. So first, we have the determinant of A now is equal to A, why did I put A13? First row, third column. Oh yeah, it is. Okay, first row, third column. So A13, C13. Now we want the second row, third column times C23. Third row, third column, A33 times C33, and then fourth row, third column, C43. These entries, A22, A33, A43, are all 0, so we're left with A13, C13. Our C, we take our negative 1 raised to the 1 plus 3, which is 4, times the matrix A13. And that was an alarm over here, so anyway, A13, first row, third column, that's the 2. And our negative 1 to the fourth is 1, and then A13, so that's first row, third column, deleted. So that's the matrix 0, negative 5, 0, 3, negative 8, 5, and negative 4, 3, negative 6. So now again, because there are two zeros here, we're going to expand along the first column. So we have our 2 times first column. So A11, C11, A21, C21, A31, C13, and A11 and A31 are 0. So we're left with 2 times A21, which is negative 5, and then our negative 1 to the 2 plus 1 is 3, and then A21 plus 0. So this is going to be 2 times, this will be positive 5, which is, I'm sorry, negative 5, so that's negative 10, A21. So A21, so delete the second row, first column, and we're left with negative 10, 3, negative 4 over here, and 5, negative 6. Now this is why is this, okay, 10, and then 3 times negative 6 is negative 18, 4 times 5, this would be a minus, so that's positive 20, which is equal to 20. So somehow I got this negative 10 here. Why is that? Oh, this should have been a positive because this is negative, so there we go. So this should have been a positive, this should have been a positive. So there is our answer. Yes, I had said that with the question because I'd lost track of where I was, but yes, there is our answer, 20. To review what we had covered, we talked about determinants. We did our definition of the determinant of the 2 by 2 matrix given this formula. We talked about how for greater than n equals 2 we had this recurrence kind of formula where we take the negative, first we expanded on the first row, negative or positive a sub 1j times the matrix a sub 1j. Then we also learned about cofactors and expanding along any row or any column. And we talked about the determinant of a triangular matrix, which is just the product of the entries on the main diagonal. So that's it for this video. Thank you for watching.